This is ferrofluid, a colloidal liquid with tiny ferromagnetic particles suspended in a fluid that, in the presence of a magnetic field, forms peaks and troughs. Those peaks and troughs align with the magnetic field. It's pretty cool stuff, and it can highlight some important principles about ferromagnetics and electromagnets, the focus of this video. First off, I'll explain a few things about magnets. Magnets have two poles, a north pole and a south pole. Unlike poles attract, while like poles repel. If you split a magnet in half, you get two magnets, which will each have a north pole and a south pole, and not two monopoles. To better explain what I've just said, I've labeled the top and bottoms of these two magnets with either an N for north or an S for south, depending on whether the two ends attract or repel one another. Like I stated before, like poles repel and unlike poles attract. Here is just another example of that principle, but this time showing what I've labeled as the south poles. And here's a few slow-mos for your enjoyment. Just a bit ago, I mentioned briefly that splitting a magnet in half would create two magnets and not two monopoles. I just wanted to take a moment and explain some more about that. Monopoles don't exist, or at least they have not been observed. What we do observe is that splitting a magnet in half gives us two magnets. To have a monopole would be like breaking a magnet in half and ending up with an isolated north pole on one half and an isolated south pole on the other. Since there would be no field lines, since the one half would be only either a north or south pole, current would not be able to flow. Since we define the source of all magnetism as current, there would be no magnetism. The lack of magnetism in a material such as iron is not due to the absence of current or field lines. In other words, it is not due to the presence of monopoles, but rather it is due to the random arrangement of tiny domains in the material, each with a north and south pole, which cancel each other out and result in a lack of magnetism. More about that will be explained later. This shows what actually happens when a magnet is split into two parts. You get two magnets. You can continue splitting the magnet into smaller and smaller pieces, and if you were to continue to do so all the way down to a single atom of iron, if that's what your magnet is made out of, then even then, with a single atom, will you continue to have a north and south pole. Ferromagnets get their name from the Latin word ferrum, meaning iron. Other metals such as nickel, cobalt, gadolinium, and neodymium also fit the bill as ferromagnets. I have here a couple of neodymium magnets, which as you can see are quite strong. Now initially you could go out in the mountains and find a piece of iron, and while it may stick to a magnet, it itself may not be magnetic. This of course can be changed rather simply by placing the piece of iron in between a north and south magnetic pole, and heating and tapping your piece of iron. Once cooled, the two magnets on either side can be removed, and you will have magnetized your piece of iron. Since you still have the same piece of iron, it begs the question as to what exactly occurred in that process. The answer is quite simple. Tiny regions or domains of the piece of iron were initially arranged randomly, canceling out any outstanding magnetic fields. But upon placement in between a north and south pole, and upon heating and tapping, those domains grew and aligned more uniformly, resulting in a magnetized piece of iron, which you can now do cool stuff with. This is just showing that throughout the process of making your magnet, your piece of iron should be placed between a north and a south pole. If you wanted to return your piece of iron to its unmagnetized state, you would simply need to heat it above its Curie temperature, the temperature above which your magnetized piece of iron would become unmagnetized due to the increased energy and movement and the domains once again becoming randomized. Electromagnets are different from ferromagnets, although they employ similar principles. Electromagnets make use of electric current to create a magnet. They are not permanent magnets like ferromagnets, but are rather temporarily induced to exhibit magnetic characteristics. They are found in MRI machines, wrecking yard cranes, and particle accelerators. Electromagnets, like ferromagnets, have a north and south pole, which can't be separated into monopoles, and again, unlike poles attract, while like poles repel. Ferromagnets and electromagnets can be combined to create really strong magnets, which can come in handy when really strong magnet effects are needed, like with wrecking yard cranes or particle accelerators. This is a side-by-side comparison of an electromagnet and a ferromagnet, illustrating the concept that the shape of their magnetic fields are very similar. Iron filings in close proximity to either an electromagnet or a ferromagnet would align with the magnet's magnetic field and allow the viewer to, in a sense, see the magnetic field lines. Some differences include that with the electromagnet, the iron filings would collect inside the coil. That is not to say the same would not happen for the ferromagnet. It would, but if the magnet is not hollow, then the core of the magnet itself gets in the way. Another difference between the two is that the electromagnet is comprised of a coil with a current running through it, whereas the ferromagnet is a permanent magnet with domains that are more or less in alignment with each other. Before we get to messing around with ferrofluid, it should be noted that the source of all magnetism is current. An electric current gives electromagnets their magnetic properties, and the spinning of an unpaired electron around its nucleus lends ferromagnetics theirs. As you can see, the two magnets have unlike poles, and so they attract. And depending on how close I bring one to the other, they attract differently. If I pull one away from the glass, then it is attracted more to the one that's across from it, since that one is closer to it now. In this video, it is pretty cool to see how, even with a small amount of the ferrofluid, as the magnet is brought closer to the glass and therefore closer to the ferrofluid divides into smaller and smaller pieces to align with the more magnetic field lines that it is experiencing. In this video, it is pretty cool to watch how, as I bring two magnets that have like charges, so they repel, the ferrofluid also does likewise. And as we learned how magnetic field lines never cross, you can see how the ferrofluid kind of leaves that space in between the two magnets until they get close enough, and then some does cross over. I'm not exactly sure what's going on there, but it's still pretty cool.